what if we can understand the human brain? And what if we can understand the universe? From our worldview, math is AGI because that is like the starting point of reasoning. People just realize that hallucinations getting bad and you need a reasoning model. So I think around the time of 2022 or 2023, I kind of looked into like from what they're improving. My main motivation has never been about hallucination because I know that's going to be like a controlled problem. Just from like a law of physics perspective, humanity is not going to let this level of BS hallucination happen forever.
Welcome to Founded and Funded. I'm Madrona Managing Director Matt McIlwain. Today I'm delighted to be here with Carina Hong, who's the founder of Axiom Math, a company focused on building self-improving superintelligent reasoners. The company's at the frontier of AI. And Carina and her team are working on one of the most ambitious problems in technology today, building towards artificial general intelligence by grounding AI in mathematics and enabling a hallucination-free proofed style of reasoning. At Axiom, her approach trains systems on formal mathematical proofs so they can move beyond pattern matching to superintelligence that is verifiable, reliable, and correct. In this conversation, Carina's expertise is going to allow us to unpack what AGI truly means. We're going to explore how to think about reasoning as the foundation of intelligence, what progress in math-based systems reveals about the future of AI, the technical milestones that are reshaping companies and what they can build, and what leaders should be doing to pay attention to how technology evolves. With that, let's dive in. To me, what's interesting, having been an investor from day one in Axiom Math, is there are these debates about what is artificial general intelligence and what is artificial superintelligence. Curious how you define, and whether you choose to define it as AGI or ASI, how you define that, and then we'll go from there.
Thanks, Matt. This is always just great to chat with you. I feel like the word AGI actually currently, it has this emotion element in it. It's the belief that reasoning capability can be so abundant and that you can have copies of any genius you pick in the world. And it compounds from there. Like you have these genius kind of like work with each other, collaborate, and then ideas like fuse between different scientific fields. And then that capability then trickles down to the day-to-day life for ordinary Joe to enjoy the same amount of capability and speed of knowledge discovery, generation, and also like applications. So that's like, I think a lot of people, when, they say we are like AGI pilled, that's what they mean. Mm-hmm. They believe that future is going to come. Then there are also other people who define AGI as more practically, when that capability really kind of like flows through everyone's consumer's day-to-day life and enterprise workflow, because I think we're quite ahead in the capability. And there are so many people building applications, which is great, but it's not like a time that someone, say in Alabama, would use whatever that is the most like state-of-the-art coding model,
yes.
And say UN code verification tool to build a project that is in their passion. Like, we're not there yet.
Yeah, I was just in Georgia last week, and I think people are using the state-of-the-art of AI without realizing they're using the state-of-the-art of AI. And of course, as you know, and we'll talk about, the state-of-the-art is moving rapidly.
That's right.
So you've made this provocative statement that math is AGI. What does that mean, and what should we take about the statement?
Yeah, I think that is the DNA of Axiom. Right? We're like very clear that in the future, we're going to see so many promising markets. The first one is best first is verification. In the future, we're going to see more markets, but the DNA of the company remains math. And in our view, we think that from math and code, which if you understand it in a sort of Curry Howard way, they are actually twin. You can then do a lot of things in the kind of use software and generation verification to control things that are in the real world, like physical engineering stuff. And then you can go to everything else. So from our worldview, math is AGI because that is right, like the starting point of reasoning. A lot of other people have different definitions about AGI. I would say that if you take the view that math is AGI, you're going to get to your, like you have your action plan, you execute that a lot faster because math is a lot cleaner. So I was on this like AI for Science conference in San Francisco. It's a really great panel and everyone is doing experiments with the physical world. And obviously the latency, of iteration is quite long. In math and, just like in coding, the digital world, your iteration time is a lot shorter. And the other thing that's really interesting is that because math is kind of like data scarce compared to the other domains. So you hit some of the roadblocks a lot faster, which allows you to debug those roadblocks. So that's, I think, one interesting difference between math and coding is that coding, we were able to make a lot of progress at the start locally, just because there's a lot of coding data.
There's a ton of data, yeah.
That's right.
Repositories everywhere.
And that's like just massive amount of data compared to, say, informal math data or like formal math data, which is even smaller.
Yeah, to say more about this math scarcity, data scarcity issue, because I think that that's one of the areas that you all are creatively trying to address.
That's right. So math is like such a data scarce domain that I think a lot of researchers at the beginning were kind of blindsided by the idea that, well, we just take whatever that has more data in math and take that research path, which is informal math. So what they do is they start scraping textbooks and papers and chain of thought reasoning data, through expert data labeling companies. And they try to basically build a math model that way. It worked for a bit. So it worked for, say, high school level, where you really just have a lot of data. And it's a lot easier to, say, find human experts around the world at the, high school international math Olympiad level than, say, at the, postdoc or junior researcher algebraic geometry level. We kind of thought a bit more first principally. We were like, well, we think we need structured data. And even if that means there isn't a lot of structured data right now, how do we invent, create structured data instead of kind of going to the unstructured route? Because today we have a lot more unstructured than structured. And the structured data looks a lot like code. I mean, it's mostly written in the theorem proving language called Lean, which has its own history, that's separate from the deep learning development timeline. And just wasn't any Lean data. And people had to kind of like hand code the undergraduate textbooks. Like they start with algebra and then they did analysis. I remember this was 2020. I was at MIT. Fast forward to, I think we started July last year. And we started under the belief that we can try to make progress on formal proving pretty fast. We were unclear what was the moment that formal math can catch up to informal math.
So take us a little bit, because there's, I think, two interesting things here. One is this idea of formal and informal AI. Let's unpack that.
It's almost like a religion.
Yeah,
like,
go ahead.
People just debate about it.
Yes.
And it's almost like I cannot convince someone who does informal math to look at the formal route. I'm like, you're missing out. You really are. And it's usually the people who are working on reinforcement learning for other domains, like coding. They know that if you do RLVR, it's incredible. They know that math is most interesting when it's proofs, and it's most interesting if you assign reward for the proof instead of just a numerical answer. So they tend to join this movement.
Some people ask the question, why now? Why is this all important today? And I usually start with, well, in a world where we're building these LLMs, which by definition are non-deterministic, they're predictive systems, you need some kind of system that's a prover, that's a verifier. How do you think about that on the why now question?
So first of all, is we could not have been early. I think that's right. Because we're seeing informal is doing pretty well.
Yes.
They are. Yeah. It's at a time where we needed to get started to play catch up in the data scarce domain. I think around the time of 2024, there's this amazing achievement of AlphaProof. And they use something called Monte Carlo tree search. That is quite an expensive system for a startup, expensive method for a startup to do. It was not clear to me that was the only way. Now, in terms of kind of why the sort of like urge to make it happen, both from my perspective and a lot of others who join us, I think it was at a time where people had more faith in structured data. So I think if we talk about the later half of 2024, people thought about coding as just another enterprise application. Coding is no difference from developing a AI financial analyst. It's no different from developing an AI McKinsey consultant. Now, obviously we know now coding is a lot different than that. I don't want to talk about recursive self-improvement, but perhaps if you can agree on at least like that is like catalytic. Yeah, that's I think the word. Catalytic, yeah. So coding does have that advantage, right? We're not far, I think, from building an AI that can do AI research. Now, the definition of that is very loose. You can define that as getting publications or even spotlight papers in ICR, ICML, and Europe's. You can also define that as being as good as one of those, researchers out there at Frontier Labs.
Yes, and some of the great researchers in academia. I was talking with our mutual friend Carlos Gestrin, and he and some of his teams have been working on some of this area of continuous learning with reinforcement learning.
Yeah, but I'm sort of like fortunate and grateful that the RL coding kind of community, they do strengthen humanity's faith in this other religion. And I think that's one reason. So the code-gen development. The other is the informal reasoner getting stronger actually also does help us. In the AI for Maths community, there's this paper called Draft Sketch and Proof. The idea is after you produce an informal proof and you try to produce like a lean sketch and you try to fill in the stories that are the voids of the lean sketch, it works better. Now, the first part is obviously beneficial if the informal models are doing better. So September 2024 was 01.
And so in a sense, it's like informal, it's iron sharpens iron.
Yeah.
They're making each other better.
That is correct. And I think that is something that Axiom sort of, we're quite, like we can talk about it a lot, right? And we're not talking about sort of the only formal Monte Carlo tree search, rigid, stiff approach. I do think that we are able to get the benefits of both systems. And I think the third thing is just like after September 2023, Lean 4 becomes a lot more workable from an engineering perspective. It is still surprisingly not workable. That's why we built Axiom Lean Engine, which is this sort of like infrastructure. There are like a dozen tools and we're adding tools to it on like a weekly basis. I believe there are like people around the world, like literally all across the world using it. And people are using it, interestingly, with their favorite model. We see, the choice of like literally any model. It can be a large language model that's off the shelf. It can be, the specialized model. Even some of our competitors model, but they use all these models with the infrastructure of Axel because it does solve a pain point that Lean is slow.
We were together the week you launched Axel,
right.
and it's incredible to see the progress.
Yeah, the growth curve of the user metric is like quite high.
And I think it's at building that ecosystem out where the iron is sharpening, iron that is, I think, going to help the whole community benefit. I love that framing, and I think for some of the folks in the audience that are like saying, okay, how much is this getting applied or beginning to be applied? This tension, as it were, between math proofs and coding. There are companies, big companies in some cases, like the Amazons and Googles that are already working on this area. You're a little bit familiar with that. Maybe talk about what they're doing and then maybe where you think the world's going.
So I think like kind of the I sometimes draw like a timeline of like verified AI. So 2016, in Google made pretty important bottoms-up strategic investment. There are good papers coming out of it. Playing with a language, theorem proving language called HOL, H-O-L. HOL list is one of the papers. And then there are like white papers, I think in 2019 by Christian Zagady, a friend of mine. When he and Tony Yu-Hua Wu, who later became XAI's co-founder, that was like 2016, 2019. And then there's Google, right, mothership. And then 2021 was DeepMind, also bottoms-up effort. One intern decides to apply this geometry. It's just personal hobby. So when this person was a high schooler, he has no interest in the other math Olympiad problems compared to his interest for geometry. So he just said, like, I just want to do geometry. And that's such a smart idea. I sometimes think of it because when I was a kid, I could never solve the geometry problem on a math Olympiad in the geometric way. There's something about my brain, and I think it's like still like now, I don't have any sense of direction. I can't envision like spatial objects. Like I can't do topology in the visual way. When I was studying algebraic geometry, I couldn't picture those like curves and like genus surfaces. It's almost like my brain is inhibited in that way. On the other hand, I overcompensate by being like the strongest algebraic brute force person you can find. I mean, like when I was a kid, I would, like eat all the inequality problems. So from a strategic point of view, I just figured out that I can express all these lines, points, intersection points, circles, triangles in like complex coordinate. And this is a brute force method. So that I just like throw away that picture. I just work with this complex coordinates and I do it the algebraic way. And it would took me like 3 times the time. But it tells you something philosophical that's not quite exactly the AI corresponding thing. But it's like, if you have a geometric figure, you can try to express it in a symbolic language. For both that human kid and in this case, this, intern of Google DeepMind. Who then that was a wildly successful project that expressed the geometry problems of IMO in the vector language, not lean, even more smaller domain specific vector language. So all these pictures suddenly become computer code. I think they later gave up on it. I don't really quite know. After AlphaProof, it was such a success, and so somehow the informal math team, Gemini, kind of had the mainstream voice, and the non-lean approach. Which is, Gemini post-training took over. They started to develop Alpha Evolve, that is discovery, construction, not proving. So we didn't quite hear much from them.
Well, I think they got pulled a little bit given some of the new model companies that were making such good progress. And they had to focus for a season on the here and now, which of course creates the opportunity for Axiom Math. So where do we go from here? Where does the field go, and then where does Axiom Math go?
I still think sometimes it's just so interesting to think about kind of why things stopped at each of these players.
Yeah, that's an interesting question.
We just covered the Google story. Yeah. The OpenAI story was just like when Ilya was there with Dan Palou and other folks, they had so many papers. It was like frequent within a couple months. Mini F2F was the high school benchmark they established. That was later sort of really trained on, contaminated by everyone, but it was one of the initial benchmarks, pointing at least a direction to go. I think there was GPT-F. They tried to have early version of GPT do F maybe stand for mathematical functions, I think. And then they just didn't. I mean, Ilya left. It just wasn't supported. Facebook was doing it. The Llama team. They spun out to be Mistral, and that was the end of story. I mean, there was Guillaume Lampo, there was Fabian. You still see some of the bottoms up meta researchers, but not really feeling like AI for Math was supported. So they came to Axiom. Great opportunity. But you just see kind of how short-lived each of these excellent projects are in the big places.
I think that probably in some of these places, the research had to be in service of what ultimately became the commercial pressures. And that perhaps a few years back, the commercial opportunity to have provers that are the complementary tension to, systems that are predictors was not quite ready for prime time, but now it is.
But why did they start it, right? So that's kind of my...
Well, I think they knew that it would come.
I see.
And it was maybe a timing question.
Oh, and they did it too early?
They did it too early.
Funny.
That's my theory.
That's really funny.
That's my theory. But now we are at this time where people realize, especially as we go from things like, chats that, okay, if it gets a little hallucinated, okay, whatever. You can go find another way to check your work. But in the world of all kinds of commercial use cases, I mean, think about hardware verification, think about software verification, think about a transactional verification or a security use case. You want some certainty that's going to counterweight the predictability of the, as we think of them today, LLMs.
It's shocking to see how many people are using Axel to verify things in blockchain. This
Interesting.
is just like, we're just seeing, wow, like all these interesting use cases coming
And a blockchain supposedly is provable. I mean, in and of itself, right?
Yeah.
The system is supposed to be provable.
Yeah, smart contracts.
Right.
Yeah.
Right.
I do think it's interesting because it's like the benefit of being in a startup. It declares DNA. Hopefully it's doing well. Is that you have actually that research security.
Yeah, that's interesting.
Like you're the core engineering group. You're pushing on something that is on the critical path. And that critical path like does not waver. Like we're talking about like years of good work and at a sort of like, prime stage of this researcher's career. And it just compound from there. Like after a win, unlike in some other company, there's rifting coming. Like you have finally reached that. So your point of too early is so funny. It's like they have outdone themselves.
They have outdone themselves. And I think
should be forced to pivot.
The researchers that I have loved getting to know the most are doing research for impact. And I think at Axiom Math, you are bringing people onto the team that are excited about research for research sake and impact. It's an and equation.
Yeah.
So tell us about the Putnam competition from last December and how this came about.
That's right. So I think early stage startup, people get excited by a common goal. And for us, that goal, that sort of mission was Putnam. Putnam exam is very hard. So I think if people choose Putnam, that generally mean one, they have taken that exam, which we found a lot of people who's like Math Olympiad, trajectory stop at the high school level. And two, they're not like totally, hopeless yet. So a lot of people go to Putnam and more than 50% will get a 0 out of 120. So
that's discouraging because these are very, very bright people. And to get a 0.
And you have partial credit. You have still like more than 50% of about 4,000 participants each year that are representing their respective universities. The Putnam teams got a 0.
And so many, many people are getting 0 out of 120.
Yeah.
And there's only been a few people that have ever gotten a perfect score.
Out of, I think, 99 years of Putnam, there are 5 human perfect scores. We got a perfect score, and this is an AI perfect score. And this is just quite, I think, striking, even from our perspective. I personally did not do that well. I got like 39, so not even 40, and I got an award for it.
Wow.
Yeah, so...
So how did you prepare for your systems to take on the Putnam test?
Surprisingly, a pretty hard part was aligning on this goal. Just because people were like, well, this is quite hard. I mean, you probably hope to, start with a high school real-time tournament. But timing-wise, there just weren't any. So we started on the day of the International Math Olympiad when we had no money. So the company literally just operated that week. I mean, we had camping chairs, foldable tables. We didn't have a line of software written.
Perfect startup dynamic.
Yeah, so we didn't have such a high school tournament to hill climb before Putnam. The other thing was later we realized that this year's Putnam, the 120 perfect score is hard for 2 reasons. First, top performing human of this year is 110. And the best informal LLM, sort of like general off-the-shelf models, is DeepSeek, 103. So this is the first time in formal AI beats an informal one in a data scarce sort of like disadvantage kind of starting game.
I think related to this is this whole idea that, the pace of innovation is, I've never seen it, and being in venture for over 25 years, the pace of change. You've been so deeply involved in this area, for the last several years. How are you seeing the pace of development in applied AI and where it's going and the research?
So I think generally progress happens for like a couple of reasons. Some are random, some are not. The sort of random reasons are like somehow people start believing, buying in a religion. So I think if you think about how many companies are pitching continual learning after the Ilya Kisper podcast, you see, you can call that like a Ilya surge.
Yes.
continual learning, people have been pushing it since like forever. Before the AI people got interested in it, the neuro AI people were quite interested in it as well, just because of a meta learning sort of in the cognitive science literature. Well, interestingly, I think they were studying why it was hard. I did my master at Oxford Neuroscience, and one of my master dissertations actually on continual learning, but from the angle of like why it's hard, like from a theoretical perspective. Obviously, that's not going to make things easier, better on the practical side. And there are like some other not so random reasons, which is like people just realize that hallucinations getting bad and you need a reasoning model. I mean, that is just, as plain as it then. So I think around the time of 2022 or 2023, I kind of looked into like from what they're improving. My main motivation has never been about hallucination. It just has never been, because I know that's gonna be like a controlled problem. Like just from like a law of physics perspective, humanity is not gonna let this level of like BS hallucination happen forever. Right?
Yeah, it's almost like the benefit of having systems that can hallucinate.
That's right.
Is that in a sense they can be creative.
Yeah.
But the risk of a system that hallucinates is that you can't prove it
wasn't
provably
even
true.
Back then, it wasn't even creative. But I think it's like also you can choose to build contractually, kind of like kind of controlling the downside. Yep. You can also build expensively. And I'm always like the kind of people that's like kind of in favor of expanding the universe choice, like for both myself and others. Like I kind of jump around in academic disciplines. I do whatever I want.
Yep.
I don't question why I'm suited to do it. And in that sense, right, like what my interest in formal theorem proving has always been like expensively. It's like, well, what if we can understand the human brain? And what if we can understand the universe?
And as you pointed out, I mean, this field, if we'll call it artificial intelligence, actually, it's almost the exact 70th year anniversary of that. There was a gathering at my alma mater, Dartmouth College, in the summer of 1956. And these different pathways
1956
around 1956.
Wow.
And these different pathways are now, in some ways in contention with each other. But I really believe, and I think you believe, that they're each pushing each other at a pace that we've never seen before. And that leads to lots of debates. Reasoning systems, continuous learning, where do we get most of the benefit? There's been a mindset of, pre-training was dead. That it was all over. It was all going to be in post-training. And then it was all going to be, continuous. And now we're kind of coming back around and saying, wait a minute, some of the newest models.
I had that line in our initial seed round pitch deck.
I think you did. I think you did.
Like it was, I think something like skilling is dead, but long live skilling.
Ah, yes. I like that
framing. The point was like, it wasn't skilling is dead, is that we want to scale formal data.
Mm-hmm.
And it was just like it was fascinating,
And that was a year ago.
Yeah.
Right.
Yeah.
And so
that was so bad. That's my point. Like I would have put it in today.
Well, it's a fun way to catch people's attention.
That's right. It's like, clickbait.
So people are curious, I'm sure, how you're thinking about, okay, so we're building these really interesting models. We're succeeding at the Putnam competition. What are the commercial use cases you're exploring? What might a verification system be able to do?
I think very sort of specific call to action is I call everyone who wants to reimagine the EDA space to just come and join us. That's one. I would say that we have learned a lot in the hardware verification space, thanks to a lot of subject matter experts, both in terms of like potential customers and in terms of people who have been working in the field and wanted to be done differently. I think that a lot of the SMT-based formal checking tools are widely used. They are widely used, but they are, not sort of, they cannot make it autonomous in a way where you need humans to do some hand-holding, adjusting the control value to a smaller amount where it does not suffer from the complexity, explosion. So we have learned a lot in the hardware verification space. I think the dream really is to, if you think about verification cycles being 3 to 4 times design cycle in time and 3 to 4 times number of people in like headcount than design team, then surely there's something that needs to be improved, right? And then, a big sort of question here is, are these existing formal checking tools good enough for the sort of more elastic demand future? And what we have found is that lean theorem prover could verify circuits that formal checker could not.
Wow, that's a big learning.
Yeah, not an entire gigantic chip yet. I want to kind of like qualify this, but it is a small local part of the circuit that is still too large for those formal checker. So this is some sort of, interesting margin or gain that we are observing. And another thing I would say that's also interesting, counterintuitive, is the proof of that case is hundreds of lines of lean code, when most of our Putnam problems are thousands of lines of lean code. And in some of our research problems, tens of thousands of lines of lean code. So I think it is possible that we could have not one Putnam and be able to serve these customers. So that is interesting, right? It is the sort of sender capability overhang that we observe in just across AI, but it doesn't mean we shouldn't win Putnam, because we it's frankly quite fun, and I think that there could be a lot of reason why you want to push on the mass theorem proving capability side, because of software verification. So what we have found is, I think we have one of the strongest mass prover in the world. And that also corroborates with, we saturated the code Verina benchmark, a lean software verification benchmark. I think DeepSeek prover was at 11-12%. Godot prover is at 11-12%. We're 98.93%.
That's incredible. Yeah. And I think this is part of what you're beginning to learn, is that being able to build verification systems, prover systems, can be generalizable at some level, and not only generalizable, but then, order of magnitude better.
Yes, and I could argue something that's interesting, right? Which is like, if you think about, hey, I just don't have an affinity for math, supposedly, right? I just don't care about math. Like, this is like a very sort of like extreme brainstorming exercise. And I want to train a model that can do all these things. So I will need to collect some hardware data. I will then need to collect some like software data. And all these data have commercial value sort of like attached to it, versus math is kind of free. So if you train on like math data and it transfers quite efficiently to these domains, then this is sort of generalizable, not universally, because you can't make a good writer or poet out of it, but it's generalizable in the best way, in that you are taking a short, efficient path to tackle some of the most valuable domains where you might not have a data moat if you just pursue those domains.
No, I think that makes sense. So let's come back a little bit then to this question of, what does this mean for the definition of artificial general intelligence, artificial superintelligence? How do we put all these things we've been talking about in the context of math prover systems into that broader world?
So think about the word like Gen AI applications, right? And like, so there's this like internet meme of like, they're like a huge building, like a lot of bricks, all these like stuff. And then like there's only like two pillars, like literally just two bricks here and there. And there's like all these stuff like on top of it. And these two pillars, in my view right now, the infrastructure layer is LLM and predictive analytics. Nothing else. The whole world of Gen AI built on probabilistic LLM that we don't understand and predictive analytics. So it's just from a symmetry standpoint, Matt, like just from a symmetry standpoint, if you have such a stochastic system, it makes sense for you to have some deterministic
system
component. It just from a symmetric. So then we want to basically we think of ourselves as this sort of addition, an inevitable addition in all possible future in the AI infra layer.
Yeah, you need determinism in a world of non-determinism.
Yeah. I will add something that is another, I like symmetry. I think it's a beautiful concept. Like in group theory, you have symmetry everywhere. Another symmetry here is, isn't it beautiful that you can express math in code and you can verify code with math.
I love that.
I think that is just beautiful because it's like, in a way, there is a very clear path in front of us to unify the two pillars of the digital world. I kind of agree by so many experts, like Eric Schmidt talk about it all day. Two pillars digital world, math and programming. Math and programming. Programming gives you output. Math gives you property. And output is meaningless if you don't know what property is satisfied. Like my age is a number. Yeah. That property is it is my age. I mean, it is in that sense, like you have logic and you have computation. And they're unified, I think, in what we're doing, what we're set out to do. So I think that's something that kind of oriented to today's AI landscape, but there's a future one.
Which maybe brings me to one last question, which is, in less than a year, you've already built this incredible team with complementary coding and math and infrastructure and a whole set of capabilities. How have you been able to do that? And what are you learning, from being a founder and company builder and team builder?
There are a few theories I have. One is like, it could be that just formal math was so data poor. It's like, this plant is almost dead, but then you just water it and it like has beautiful flowers coming out of it. That's one theory, right? Which means very good sample efficiency, right? Like that's kind of the technical sort of idea is that if you have verified output pairs, then grounding the natural language, have formal logic, ground the natural language, you're going to do like really, really, really well. In terms of sort of like the other sort of team building aspect, I think sometimes, and this is quite encouraging, when I was talking to folks like François Charton, for example, and Ken Ono, I felt like it was like there is a shared dream and there is this like shared yearning. Some people don't state it. Some people state it. That is that we all yearn for a superhuman mathematician. And this is like very interesting because if you think about like, in the context of like job replacement, say in like, if you have like a superhuman AI lawyer, that means some lawyer is going to be out of job. And some lawyers might be like averse to that. Math is a field where there is a common goal where people are aligned around, and that is the pursuit of knowledge. And so it's like, if that is a common goal, there isn't a lot of ego around who's going to make it happen. And the feeling of being able to call yourself, you're a great mathematician, and extend yourself and clone someone who has passed away decades and centuries ago and talk to that. These are, I think, beautiful sort of like concepts that somehow, because of technical reasons we have talked about, are coming into life. And what are we seeing every day, right? We're seeing, and this is maybe why people feel motivated to work even harder. We're seeing every day is like, we will like get an email about a math problem from say like a professor in Germany that is in Ken's network at 10 a.m. By 2 p.m., 4 hours later, Axiom Prover generated a whole link proof without human intervention.
Yeah. Autonomously.
Autonomously checked, send it back to that professor. Like, here is a proof to your unsolved math problem. And that is daily mathematical Pokemon hunting in our sort of like, in a funny way. But there's something deeper, and we're still slow to react to that fact.
You're learning your way through that.
We're slow to react to that fact that there is hardware and software verification. I think there is endless market that is in the category of mathematical superintelligence.
Well, that shared mission about mathematical superintelligence, the incredible team you're building, and this ongoing curiosity to discover what the use cases are for that to impact the world is what's inspired us to be partners and colleagues with you.
I don't know if last time I saw you, I told you this news, but so like, just there are mathematical results that after I tell people, they're like, I don't really know how to like technically prove it, but it sounds beautiful. And here's one. It's something recently autonomously proved by Axiom Prover. So The Ramanujan tau function is, tau, and it is a function that appears frequently in Ramanujan's lost notebook. It's one of the fundamental functions in number theory. Axiom Prover, the AI, autonomously proved that the Ramanujan tau function misses 100% of the primes.
Wow.
And this is assuming the ABC conjecture, of course, which is something like the Riemann hypothesis. A lot of people, or generalized Riemann hypothesis, people just agree or assume on. But this is something that we don't know. And so that is a beautiful result. I mean, just when we shared it, people felt like that is, I like to be this math evangelist because I just like talking about it. Relatedly, there are mathematicians like Ramanujan in this case, and Miriam Mazzacani. They left, behind like bodies of work, in terms of Mazzacani, there is the dynamical systems. And recently there is a paper that we published that is U-Michigan professor Alex Wright posed the problem. And in that case, we were able to auto-formalize the solution. So like verify it is correct and actually optimize the proof and corrected the proof mistakes. So comes in different forms, some autonomous proving, some auto-formalization. But we're at a point where we have, I think, 7 papers on arXiv now.
Wow.
Where the main engine is done by Axiom Prover. I think 5 for proving and 2 for auto-formalization.
Well, I'm excited about this idea of the beauty of math and the applied beauty of math that Axiom, you, Carina, and your team are going to help us discover in the years ahead.
Thanks,
so thanks
Matt.
so much for being here with me today.
It's really
enjoyed
great.
the conversation.
Thank you.